Okay, so for the last part of your calculations components for this chapter itself, we're going to talk about your power. Now, when we talk about power or when we talk about something is powerful itself, how do you know if someone is very, very powerful? So basically, for example, the task is to lift something up very heavy or to move a very heavy object from point A to point B itself. Power, if you know that this person is powerful, very strong, very powerful, he can do the action in like a very short amount of time and achieve what you want. However, a weak person, maybe he needs to keep dragging the object on the floor and keep doing that. It'll take a long time. So keyword that is actually linked about power is about the amount of time you take. Is the rate of how much energy that you use, how much work you have done. Okay, so power have no direction. It is actually measured in watts. So for example, power is 200 watts. Okay, capital W is just energy over time. So if you know you are powerful, if you play video games, how do you know if a character is powerful? Is if you want to defeat the boss, you just use a shot, maybe one turn, boom, one shot, you can just burst down the boss or whatsoever that you have. So in real life context itself, if you look below, if you have a power rating of 2.8 kilowatts, so we want to change it to watts itself, just times 1000, exactly the same as meters and kilometers. How much energy is transferred and your time is this. So before you start solving anything, like I always say, try to write it out in full first and convert it to your proper units. In this case, I times 60, I get 300. So with that, power is energy over time. Energy is power times time. So what's power? 2800. What's time? 300 seconds. And let's press your calculator to solve this value itself. 2800 times 300. Get a very large number of 840,000 joules. Okay, so basically this is how you familiarize yourself with it. Just remember, energy is king, it's on top. Next, your crane lift a load of 400 kg with a constant velocity. Now, this one is important now, because if velocity isn't constant, there will be changes in kinetic energy. Alright, and time taken, I took 25 seconds and I moved 30 meters. What's the power? They want to find power, right? So before we can find power itself, we need to find the amount of energy that you have. Okay, so power of the motor, I need to find the amount of energy or the amount of work done by the motor itself. So if you were to notice over here, your work done is actually linked to your energy. So in this case, it is the change in energy. Your work done is your total change in energy, right? And if you notice, I only change GPE. So how much GPE did I have? I have 400 400 kg mass, right? G is 10, H is 30 meters. So how much is this? Just press your calculator. 400 times 10 times 30. You get 120,000 joules. And power is energy over time. How long did we take? 120,000 divided by 25. 4800 watts. Which means every 1 second, I actually exert 4,800 joules of energy if I use that. Okay. Next, the battery of a lamp itself have 7.2 kilojoules inside and it can be used for a total of 8 hours. Calculate the power itself. So first things first, your energy is 7.2 kilojoules. 7,200 joules itself. Your time is 8 hours. Is 8 times 60 times 60. How long is this? 28,800 seconds. So now they want to find the power itself. Power is just energy over time. 7200 divided by 28,800. So we're going to end up with a very small number in this case. Okay, we should end up with a very nice number of 0.25 watts. So quite a very, very low powered lamp itself, but basically this is how it works. Alright. Next one, let's talk about efficiency. So the thing is, we know that in real life itself, in most cases, not all energy will be transferred to what we want to achieve. So what we want to achieve is what is usually what we call your useful energy. Store itself, usually we refer it to KE, your GPE, whatever that you want, your internal energy. basically useful energy are things that you want. So you can just imagine this is the total energy or the input, right, that you put in. Then churn, and then this is the useful part, or basically the output that you have. And you realize that there's actually some form of energy loss in between. So your useful over your total, they may not be equal. So what goes in equals to what comes out. So these two is equals to total. Okay. So in the ideal case, when you want to charge your handphone itself, you expect that all the chemical potential energy stored of the power bank is all transferred to your handphone itself, right? However, we know that actually when you actually charge your handphone with a portable bank or even your plug-in socket charger itself, your phone feels hot. If your phone feels hot, the problem is it means that some energy is transferred to your IE store itself. You are undesired heat and you waste the energy that you use. So your handphone is very hot when you're charging it. Maybe it's time to change your charger or buy a new phone itself, because the more heat that is being produced, the more energy you're actually wasting and less energy is actually used to charge your handphone itself. So your handphone actually needs a long time to actually charge the handphone, because most of, or even some of the energy is actually used to just produce heat, which is not what you want, right? You just want to charge your phone. I don't want heat. But in your day-to-day life itself, in real world application, most of the time when we use any kind of application or charge our handphone, there will be some form of energy loss. It will never be perfect. Okay, so because of that, we need to learn about efficiency. Now, if you were to notice, it is useful over total, or you can also write it is your output over input. Now, if you notice, we can either use energy or power. So it's actually quite interchangeable. If the question gives you energy, then we'll use energy. If the question gives us power, then we'll use power. So quite flexible in this case. Now, let's take a look over here. Now, your engines, they usually burn fuel like petrol to produce a force. Your efficiency is actually quite low, 20%. Okay, so full tank, use this one. This is your input. Okay, input is 1.5 gigajoules, which means 1.5 times 10 to the power of giga is 9. Very big number. Okay, so your useful is 20% of input. So your not useful is therefore 80% of input. So how much is 80% of input? So which is 0.80 times 1.5 times 10 to the power of 9. How much is this? Okay, this is actually 1.2 times 10 to the power of 9 joules. Okay, so this is the amount of energy that you waste that is not being used by the. Okay, so moving on to question 2 itself, a man can actually exert a force. Now, if you were to notice, just now, if you recall, right, conservation of energy, the whole equations and all that, then you notice, where does this work done or work done by the man, work done on the box, where does it come in? It comes in at the very start. So you can see at this stage, this is your initial state. This stage is your final stage. So initial and final itself, okay? So how much energy is transferred to the block? To the block, right? Ask yourself, he's actually doing work on the block. So this is actually a work done question. How much force is he exerting on the box? He exerts 30 newtons and he pushes it 6. So in this case, 180 joules. How much is in the kinetic energy store of the box? How much is in the KE store? So this one is actually talking about this part here. So KE half mv squared. Now this is different from the previous question because this is actually a calculate question. So we have to use a formula to go and calculate it. So let me just clean it up nicely. Half times mass is 8 kg, V6 square. Don't forget the square. 0.5 times 8 times 6 square will give us 144 joules. So what is the amount of energy dissipated? If you don't know what is dissipated, it means loss. Okay, so you can see, right, the equation is at the start, what energy do I have? I have the work done on the box. And what energy do I have at the end? I have your kinetic energy plus energy loss. Okay, so let me just bring this up. So your energy loss will therefore be my 180 joules minus 144. I should end up with 36 joules over here. Okay, so when you talk about efficiency, what is your useful? Useful is the kinetic energy, right? So it's KE over the work done times 100%. So kinetic energy is 144, total is 180 times 100%. How much do we get? We actually get 80%. So this is 80% efficient when he's actually pushing the block itself. So why is energy dissipated? So you can just say that some energy is transferred mechanically from the kinetic store of the block to the internal of the surroundings due to frictional forces. Okay, so that is why some energy is actually lost. So that is what happens, because if you notice, the question doesn't mention anything about your work done, nothing about friction, nothing about any kind of energy loss itself. So you can just mention this. So actually the front part can be worth 1 mark, and then the last part is the reason why you also get 1 mark itself. If you want to elaborate further, it's perfectly fine as well. You can talk about air resistance, you can talk about when the guy is pushing, he's also, there's some energy loss from there, but basically the gist or the most straightforward explanation would be this. Okay.